Awesome. So I have a lot of information to get through. So I'm just going to get right into it. This is specifically about trustless interoperability between L2s. Bit of a wordy title, so I've just decided to keep it here. But basically, the motivation for this talk today is when I joined the space somewhat recently, I decided to kind of look at the interoperability problem immediately. And right upon doing so, you can see everybody kind of has different definitions for how they talk about these things. We see atomic inclusion, atomic composability, synchronous atomic composability, asynchronous composability. These are very confusing things. So my aim today is to sort of clear this up and figure out what we actually need to make these things happen. So I came up with what I call the 6-level framework for discussing interoperability trustlessly. This is a broad overview. In the interest of time, I'm going to move beyond this, but I'll give you a second to take some photos and just get an understanding of what is sort of the impact of each of these levels. So getting right into it, this is the default case. This is what we have right now. If you want to move between rollups, you can't really interop. You have to withdraw. You have to wait. Once your funds are out, then you can deposit in the next destination rollup that you want to go to. But this sucks. Atomic inclusion. This is where things start to get a little bit more interesting. I think the way to understand this is we have a bundle of transactions and we have some shared sequencer that can guarantee inclusion, but it can't tell us whether things are going to execute successfully or not. So we can see over in the bottom here, rollup B might revert one of the transactions. So the impact of this is that it's actually really difficult to take advantage of any sort of system with just atomic inclusion guarantees, because if you want to create a bundle of dependent transactions, you can't, because if one reverts, then this is going to have issues on the whole system. So the necessary infrastructure would be somewhat of a lazy shared sequencer, and we can go into the technical nuances after if you have questions. So I'll just keep moving on. The third layer is where things definitely get a lot more interesting. This is shared settlement, and this is what we're going to see a lot of in the next year. So things like the AG layer for Polygon, ZK Syncs, Elastic Chain, Superchain, they are all doing this. And the definition is having multiple rollups all settle to the same shared bridge contract. There's usually a proof aggregation step involved in the middle as well, but that's technically not necessary, and we'll get into why maybe afterward. And so the advantages and capabilities of having shared settlement is that you don't have to wrap assets to go across chain. Because we're sharing the same bridge contract, we don't have to worry about managing the accounting on all these different bridge contracts on the L1, so that's great. We can go native ETH to ETH, and that's all in the protocol, no bridging required. So we need a shared bridge contract. We optionally need relays. Again, not going to get into the nuance of that. And we need proof aggregation to do this as well. So next we have atomic execution. And the idea here is the exact same as atomic inclusion, but now we can guarantee that these transactions will execute. And when I say execute, that means they're going to create the required state change that they were intended to create on the chain that they were intended to go to. And this is really, really important because now for things like cross rollup arbitrage, we have guarantees. If you don't have guarantees, you might get involved in a case where one of your arbitrage transactions goes through, the other does not. You don't actually profit. People do this right now. This is kind of what SexDex ARB is for the most part. I mean, if you don't get top of block space, but it's suboptimal. So we want to have something like this that guarantees that transaction bundle to go through. And now we start to need more shared components in the middle. We need a shared sequencer. We need a super builder. Technically, talk to me after. And a soft finality layer. Technically, talk to me after. This is where I want to spend a little bit more time. So this is what I think should be the goal, for now, at least. And this is block level composability. This is a really crazy diagram, and I'm not going to go through every single step of it right now. But basically, the idea here is that we can compose between rollups within a single block. So a lot of times on Twitter, you'll see people talking about, oh, we need synchronous composability. What does that mean? This is one way that they mean that, where you can have this dependent cross rollup bundle of transactions. And this is really important because now you can do things like single block cross rollup swaps and limit orders trustlessly. And the trustless component means that you don't need a liquidity bridge, you don't need to trust any sketchy intermediaries. You can do this all with minting and burning in a safe way. You do need a shared sequencer or a super builder. Again, I keep, we'll talk after if you're curious about why I keep going or super builder. It's actually pretty nuanced and really interesting. And then the soft confirmation layer, again, not strictly necessary, but this ensures the validity of the bundles. So you can think about creating this cross roll-up bundle of dependent transactions as a somewhat risky thing to do, but if you have this soft confirmation layer that ensures, hey, all of these transactions were well formed and we've simulated them, we can give a pre-confirmation on that bundle so we can ensure that we can do what we want to do. This is the final step, and this is technically the holy grail of cross roll-up interaction. This is basically a smart contract to smart contract layer of interop for these rollups. Now, the really interesting thing about this case is that it basically ensures that any state change prior to any call can be reverted if the call reverts. So this is what we want in smart contracts right now. You make a call out to another smart contract, the call reverts for whatever reason. Any state change that happened prior to that call must also be reverted. And that's really, really important for the developer experience because you can't take advantage of any cross rollup opportunities if you don't have that, because you don't want to act on state that did not occur in the domain that you wanted it to occur in. So this would be like the holy grail, best case version. This is amazing, but it's really difficult to get. And yeah, so the advantages and capabilities, smart contract-like experience across all rollups. This is amazing. We can guarantee that any state change can be reverted. Cross rollup flash loans are possible. We need VM level changes. We need a shared sequencer. We need super builder. We kind of need as much shared state as possible without literally being on the same rollup. So what's the takeaway? Block level composability is the right goal. We should not be optimizing for cross-chain flash loans. We need shared state to compose, so we need a shared sequencer, we need a shared super builder, some sort of shared state to go back and forth here. And the last point, I've got 7 seconds left. Rollup clusters, you're gonna hear a lot of people talk badly about these because they're walled gardens. They're fantastic. They're really good for the middle ground, and we're gonna work up to a place where we can bridge between all of them. So thank you.
Thank you, Marshall. That's it. We are not taking questions. If you